Physics episode on gravitation and orbital motion. In previous episodes, I have introduced Newton's Universal Law of Gravitation, and we've done things like, find the new acceleration due to gravity on a different planet of the solar system. This time, I'm going to be looking more into how orbital motion comes about from putting centripetal force together with Newton's Law of Gravitation. We're also going to apply some conservation of angular momentum to look into elliptical orbits, so orbits that aren't quite circular. Just to start off though, get a little taste back for Newton's Universal Law of Gravitation, and that is just stated out that the gravity, the attractive force between two masses, relates to the gravitation constant G, mass 1, mass 2, over r squared. There's the inverse square law in there that relates the two masses' forces. Okay, so just a reminder, G is a very small number, rounds to about 6.67 times 10 to the negative 11. Of course, there's some wonderful units in there that make the force into newtons. This is the value that we use to convert that. And now let's say, let's give a little scenario here so we can work this out. Let's say, what is the acceleration due to gravity on a particular planet, extrasolar planet, that is determined to be about the same density as Earth, but twice its radius. So R is, for this new planet, twice Earth's radius, but the density is the same as Earth's density. And that just speaks a little bit to the mass, so we just refer back to get to that mass of the new planet. Now, what character are we looking for here for G? Just as a reminder that the gravitational force is also mg for a mass at the surface. And that's what we're looking at here. What is the acceleration due to gravity for a mass at the surface of this new extrasolar planet that's not attached to our sun gravitationally? So, so this is mass at the surface. If we were to compare these two, what that means is if one of these masses over here is also the mass at the surface of the planet, that means M1 is the mass of the planet itself. And you can kind of eyeball it here, this conglomeration of the mass of the planet over the radius of the planet squared, all of that is what G is about. G is equal to the big G, gravitation constant, as mass of the planet over radius of the planet squared. It is also called the gravitational field strength at the surface. So it is a vector, it's in the direction of R, actually negative R, because it goes in towards the center of the planet. Okay, there it is in vector notation. However, all we're doing is looking for a new G with these new properties. All right, so what we have so far, of course, is the constant. We don't quite know the mass of the planet yet. Let's see if we can figure that one out. And the radius of the planet is 2 times the radius of Earth. Okay, and we need to square both those values. Now back to the mass of the planet. We know that it has the same density. So since the density of any sphere, we're going to assume a spherical Earth here and a spherical planet, they're very close to spheres, is 4/3 pi r cubed. Excuse me, that's the volume. Mass over 4/3 pi r cubed. So we're looking at the mass of the planet over 4/3 pi r cubed. If we were to find the Earth's, we would need some values for that. This would be the mass of Earth and the radius of the Earth. So you can just use those as a reference there. Now for our new planet, I'll just call this P for our RP, our new planet here. We'd have the mass of the planet, which we're looking for here, and 4/3 pi times our new planet's radius cubed there. Okay. Now, since this is saying that the density of our planet, our new planet here, is the same as the density of Earth, we can set these two expressions equal. And this beautiful thing happens. A lot of things are going to drop out. And we have a relationship to the mass of Earth. We go to 4/3 pi radius of Earth cubed. And this would be, sorry, the radius of our new planet is twice the radius of Earth. Okay. It is the morning time when I'm recording this. I am liable to make small little errors here. So hopefully that'll help you think about your own problem solving and taking into account the time of the day for yourself. So a couple of these things cancel out. 4/3 pi, that'll cancel there. And we get a mass of our new planet equals mass of Earth over radius of Earth cubed. And we have down here, we've got a 2 times 2 times 2, 2 cubed, which would give us an 8 up here. Okay, there we have our massive planet. All right, and we're going to use that right up here and see what's going on with that. Oh, I also forgot the cube radius of Earth. So we have this radius of Earth cubed coming up here. I was going to say, how does a mass equal a mass divided by radius? There we go. So those do cancel out. And we get the mass of our new planet is 8 times the mass of Earth to have the same density, but twice the radius. Wow. All right. So we have that relationship now that we're looking for. And we can try this out, see what happens here. We got G, and instead of mass of the planet, we're going to plug in 8 times the mass of Earth. See how that affected there. And we had 2RE squared. Notice this one's a square, not a cubed. And what I'm going to do is start pulling out these coefficients here. 8G ME. And 2 squared is 4 RE squared. The reason I didn't plug in a bunch of mass of Earth and radius of Earth is because we're trying to compare it to Earth's gravitation acceleration due to gravity. There it is. And Earth's acceleration due to gravity, of course, is around 9.8 meters per second squared. So what about this one down here? With the same density but twice the radius, we're getting an 8 over 4. We're getting 2 times GME over RE squared, which is the acceleration due to gravity on Earth. Okay, so that's the same as 2 times 9.8. So we get a 19.6 meters per second squared. This is probably not going to be a very comfortable planet to live on. Finding a planet the same density as Earth, but bigger, will basically, as we're seeing here, if we double the radius, we're going to also double the acceleration due to gravity with the same density of the planet. We just proved it there. So that's one application of just using Newton's gravitation law with some different terms in here. Sometimes you'll get some funny things thrown at you, like different densities of planets, but that's how you work it. All right. Now what about satellites orbiting planets? Now we're going to look at circular orbits next. And if you're following along my note sheet, this is where it picks up on the note sheet with circular orbits. So first, let's take one object we know of that orbits in a circle and with a circular-like orbit. Now, even though the Earth's orbit is not perfectly circular, it does have an average orbital radius that we can use here. So we're going to take the Earth and the Sun and treat Earth's orbit as a circular orbit. Oh, definitely in the morning. I got to do a better circle than that. Come on, Shirley. Come on, Shirley. Come on, Shirley. We can do it. We can do it. We can do it. Okay, that's a little bit better. All right. This is the Sun and the Earth. There we go. There's a mutual attraction here. And as with the Earth as our satellite, and we're assuming the Sun has very little motion compared to the Earth. If you throw in all of the planets of the solar system, there is a nice wobble to the Sun. That's mainly due to the mass of Jupiter. But anyway, we're taking the Sun as a solid point, with its center as the point that the Earth is orbiting around. So as long as our orbiting body is much less in mass than the Sun, we got a circular orbit. All right, so the only force acting on Earth is that force due to gravity. And remember that the Sun has an equal and opposite force there as well. So this is a mutual force. If we look at Earth as a force diagram, that force due to gravity is the only force acting on it. But it's causing not a acceleration toward the Sun, thank goodness, but it is causing it's not causing a velocity towards the Sun. But is the acceleration towards the Sun? Definitely. That's what our force diagram shows here. Thankfully, the Earth has a tangential velocity, and it is falling forever in a circle. And that's what orbital motion is. It's projectile motion in space, where the object falls continually and never hits the surface of what it's attracted to. So we do have a tangential velocity that is tangent to the radius. It's perpendicular to the radius there, tangent to the circle. And gravity is the only force acting in towards the center. That makes gravity a centripetal force. So if we were to apply Newton's second law to Earth, the only net force acting here is a force due to gravity. And this would be Earth's mass times the acceleration. Now this acceleration is not, that's what I was trying to get to earlier, it's not making the object move faster, but it's making it change its direction. So the velocity change caused by an acceleration is a centripetal acceleration. So this is going to be a centripetal acceleration for a circular orbit. What might be our target variable here? What is our goal? Is it to find the tangential velocity of the Earth? Well, that's not very interesting. Well, let's kind of track it back to the origins of the Universal Gravitation Law. What were they trying to actually find? Well, the unknown originally was big G. You see, it was hard to take a little mass on the Earth and another little mass and find G, because while you can measure weight and you can measure the mass values of two objects on the Earth using a balance, right? You can also easily measure the distance between them. It is hard to find the weight, the force due to gravity between two objects. See, that's the problem here. Finding the weight for one object and the Earth, that's a really easy thing to measure, is weight of an object. You put it on a bathroom scale type of thing. You put a mass on the same type of scale. But if we're actually trying to figure out the force due to gravity between two masses, that weight is a very difficult thing to measure. It's very small. It's tiny. It's less than a millionth of a pound. It's minuscule. So that was the difficulty in determining G. But once G was determined, then you can apply a force to figure out the weight of an object on the Earth. You can look at the mass of the Earth, the mass of the object, okay, and mass of the object itself. And using, in 1492, Columbus sailed the ocean blue. We've been around the Earth a few times by the time this G was being studied. So we had the approximate radius of the Earth, and that means the mass of the Earth could be determined from that. So since G was determined, mass of the Earth has been determined. So what's the next step? What is our target here? We know the mass of the Earth, and that is around 5.97 times 10 to the 24 kilograms. There we go. And as experimentally determined, we have G 6.67 times 10 to the negative 11. And so what else might not be known here? Well, how about the mass of the Sun? We can't really take an object to the Sun and weigh it, so let's go for the mass of the sun. All right, so we might be able to find the velocity of Earth. That's one thing we might be able to find from this. But let's make mass of the sun our target. All right, here we go. Moving on. FG. We got mass of the Earth. We got AC. Can the mass of the sun be found? I think so. Because when we substitute in G, mass of the sun times mass of the Earth divided by orbital radius squared. Oh, there's a neat little symbol, and I just kind of botched it. It's a circle with a dot. Orbital radius. It's like the circle going to orbit around. The little dot in the center is the thing that's orbiting around. Okay. Orbital radius squared equals mass of Earth. And here we've got the acceleration, centripetal acceleration of the Earth, which relates to v squared over r. And again, the r is the orbital radius. All right, so through astronomical data, you can determine the orbital radius just by the position of the Earth at different parts of the year. And if you look that up in the text, it's 1.5 times 10 to the 11 meters. So I'm going historically. What values can we reasonably come up with here at this historical point? But again, our target is going to be the mass of the sun. All right, so we've got the mass of the Earth actually cancels out of this. Let's move ahead here. We don't really need that. Didn't even need to look that up. All right, that cancels out. And we're looking for the mass of the sun as our target. We've got G, got the orbital radius from astronomical data. And to figure out this unknown over here, we're going to need to know the velocity. Oh, crap. Are we stuck here? Or do we know something about the motion of the Earth? We know time. We know how long it takes for the Earth to traverse one circular path. It's called a year. So we actually have the orbital period of the Earth. Orbital period is 1 year. Now when we're talking about kilograms and meters per second, we need time to be in seconds. Let's do a little conversion here. Get my bars. 1 year is 365 days, approximately. And 1 day is 24 hours. And 1 hour is 3,600 seconds. You could put 60 minutes and then 1 minute is 60 seconds. Okay. So years cancel, days cancel, hours cancel. And yeah, the period in seconds is going to be quite a bit. We're going to take 1 times 365 times 24 times 3,600. And we get our number of seconds in a year. I actually have all these digits, so I'm going to use them. This looks like 31,536,000. All right, seconds. Or 3.1536 times 10 to the 7 seconds. Okay, quite a bit there. Now, what good is that? Okay, well, like I said, we got a circular path. And is this velocity constant or changing? Well, its direction's changing, but its speed is constant. And as you might recall, this tangential velocity is the orbital speed. And since it is constant, can we not just take a displacement over time? Here we have an arc displacement, an arc distance, and that arc distance is 2 pi r, the circumference of a circle. The time period is the orbital period. So the orbital period relates to the velocity by the orbital radius. And let's work that out. What is the VT here is going to be 2 pi orbital radius over the period. Okay, so let's go ahead and plug that in. G, mass of the sun, divided by the orbital radius squared. equals this conglomeration here squared, 2 pi r over t squared. And don't forget this little over 1 over r orbital there. Okay, so there's our v squared divided by r. A little bit of canceling here. First off, we've got a squared up here and 1 down there. So actually, I'll just take one of these off over here. Cancel that with one of those. I think that's a little easier. G mass of sun equals, we've got a 4 pi squared r orbital squared over orbital period squared. And ooh, I've got this r orbital over here. Thought there's going to be one more. Let's move it down a little bit. And at this point, I'm gonna bring G. Our target here is the mass of the sun. So I'm just going to leave this G mass of the sun over here for a moment. And before we move on, I'm going to bring the time period up. Bring that up to the mass of the sun and bring this radius over. I'm going to pause for some historical perspective here. Without Newton's gravitation law, Johann Kepler, one of his laws of orbiting, one of Kepler's laws of orbits, says that the square of the orbital period is proportional to the cube of the orbital radius. That's one of Kepler's laws there. Okay, without Newton's gravitation law, but Newton's gravitation law proves it, brings it out. And it might have been, Newton's gravitation law based on Kepler's law, and that's how he came up with inverse square law, that type of thing. So I think all his laws are are related. But anyhow, if we're finally going to be looking for the mass of the sun, we can find that now. Mass of the sun is 4 pi squared. Orbital radius cubed over G times orbital period squared. And those values, all those pieces, we have values for. Got 1.5 times 10 to the 11 cubed divided by G is 6.67 times 10 to the negative 11. In orbital period, we've got 2 or 3 sig figs here, so I'm going to keep that here. Here's our 3 sig figs times 10 to the 7 seconds in 1 year. And we can't forget to square that. I think it's somewhere in like 1.99 times 10 to the 30 is what the book says. And according to my calculations, I got a 2.01 times 10 to the 30 kilograms. Book value is 1.99 times 10 to the 30. Okay, so I think we're pretty close there. All right, there's mass of the sun. Determined it within less than 1% there difference. There we go. That's circular orbits. What's the main key here? Here it is, setting weight equal to centripetal acceleration. Now, what's more funner than that? Okay, I'm going to insert a page here. What's more funner than that? Well, let's put up some artificial satellites. Where should we, or let's say how fast should we make a satellite that we want to place 1,000, we'll go 100 kilometers above the surface of the planet. 100 kilometers. All right, so that's about in space, okay, about 100 kilometers. Not quite, it's really skimming skim the upper atmosphere. Some of those spheres, like magnetosphere and stuff like that. It's way up there. So we've got Earth's surface, and we want to put an object in orbit not too far above that. It's not too far out. This might be a standard orbit, something close to a standard orbit. We want an orbital radius equal to 100 kilometers above the surface. Okay, see what I did there? I'm going to have to figure that one out. 100 kilometers is 100,000 meters. And the radius of the Earth is 6.37 times 10 to the 6 meters. All right, so this is 1 times 10 to the 5. So we're going to add 1 to that. It'll be a 6.47 times 10 to the 6. My big question here is, how much speed do we need? That's a big question for people who send up rockets. We're talking about changes in velocity, changes in energy. All right, so if we change our kinetic energy from 0 to whatever, based on a certain velocity that we need, that'll give us enough energy to get into a circular orbit. That leads back to how much fuel we put in the machine, and that also leads to how much mass we got to carry up, how much rocket power do we need. So what is our orbital velocity based on that? Here we go. Again, we're going to have an object orbiting, so the only force acting on it, if we sum all the forces, equals ma. The only force acting on it is gravity. We got the mass of the object, and there's our orbital radius, tangential velocity in there. Okay, it's a centripetal acceleration. G, mass of Earth, mass of our object, divided by orbital radius squared, equals the mass of our object times its velocity. That's what we're looking for, over orbital radius. One of those cancels, and the mass cancels. So it comes down to this. Orbital velocity is the square root of what we have left over there. G, mass of the planet we're orbiting, divided by orbital radius. So this is a key feature I want you to know for circular orbits. This is a circular orbit velocity, and that makes this one kind of easy to solve. Plug in a 6.67 times 10 to the negative 11 mass of Earth divided by our orbital radius. Notice it's not squared or anything, and this is a function, just a function of orbital radius. All right, whatever velocity we want for a circular orbit. And circular orbits are really nice because you can, especially if you get a geosynchronous orbit, you can just shoot a satellite receiver, information receiver, a satellite dish, up at a certain point in space and watch it track around. All right, so we have a 6.67 times 10 to the negative 11. Mass of Earth is at 5.97 times 10 to the 24 divided by our orbital speed, or sorry, orbital radius. Be careful not to square things where you don't need to square them, and be careful to square things where you do. We'll get an orbital speed there. About 7,800. Yeah, 3 sig figs. 7,845. So we'll say 7,850 meters per second. 7.85 kilometers per second. There we go. All right, problem 1. Hubble Space Telescope orbits the Earth at a position. Well, I guess it's still up there. It's kind of retired now. Did they send that one down to burn up? I think that would be kind of sad. But it might still be up there. Actually, I think it is. They still have that operating. Moving on. So orbital velocity, as we just saw, is going to be square root of g, mass of Earth, divided by orbital radius. All right, so if we do the same thing we did just a second ago with big G, mass of Earth, we plug in an orbital radius of, it says from the Earth center, great. So that is our R. That's our R value. 6.94 times 10 to the 6th. Because remember, we needed to use meters, not kilometers. And out of that, I should be able to reuse some of my calculations here. I'll change that to 6.94. It's a higher orbit than what I just had. That's a good thing. That means we don't have rockets, and back in time it would have been the Space Shuttle Orbiter, the Space Shuttle. That'd be lower than the Hubble Space Telescope. So for that orbit, we need a velocity of 7,574. 75, let's say 70 meters per second. Let's compare those two values. For a higher orbit, we have 7,500, and lower orbit, 7,850. So you see, as you get further and further away, things can move more slowly for that circular orbit. Gravity isn't holding as much. Okay, less pull. Next one. Oh, there's no numbers in this one. The communications satellite must be put into geostationary circular orbit about the Earth's equator, meaning that it must have the same angular velocity as the Earth's rotation. And the motion must be perfectly circular so that the satellite appears to remain in a fixed position in the sky as viewed from the ground. That's why we send our satellite dish receivers and point them at one part of the sky and leave them there. They don't move. It's called a geostationary orbit. Find the orbital velocity and radius for this satellite. So we need the orbital radius and the orbital velocity. Okay, let's see what's going on here. Well, you might recall that F equals ma. So we got Gm1, G mass of Earth, mass of our satellite, divided by orbital radius squared. And that equals mass of our satellite, mv squared over r. Orbital velocity squared over orbital radius. Okay, so again, things reduce a bit, and we end up with orbital velocity being the square root of g mass of Earth over orbital radius. But we're kind of stuck here because we have g and we have mass of Earth, but we don't have the orbital radius or the velocity. So what else is it talking about here? It says it must have the same angular velocity as the Earth's rotation. As the Earth, here's the equator, as it rotates around, I hope I have the direction right, I might not. Yes, that's in the west. Yeah, it's the right rotation. This is north, that's south. Okay. What is the angular velocity? Well, we know it's related to the spin, and it spins one time around in a day. So the orbital period, not the orbital period, the rotation period is 1 day. So how many radians per second is this going to be? Well, it's going to be 2 pi radians divided by the time period. But remember, that has to be in seconds. So let's change this days to seconds. 1 day is 24 hours. Get my little bars here. And 1 hour is 3,600 seconds. All right, so 24 times 3,600 is our period. 86,400. Right? You've been waiting for something for a day. You'd be like, gosh, you're going to really make me wait another 86,400 seconds? Dang. Yeah, that sounds like a lot more, you know. If you want to be melodramatic, use that one. Okay. So we got the omega then. It's 2 pi divided by that. It's a very slow rotation. 2 pi divided by our answer. 86,400. 7.27 times 10 to the negative 5 radians per second. Man, I have to wait another 7.25 times 10 to the negative 5 radians of the Earth's rotation. Give me a second. Yeah, radians. Okay, I'm losing it. I'm losing it right here. So what's that mean? What does omega relate to? Omega relates to the tangential velocity, or tangential velocity of the outer edge of the Earth. That's where we're at. Or in this case, it's not just the Earth rotating; it's the satellite that's moving around in this circular path. So V equals R orbital times omega. And we have what VO is now. We've got this V orbital. It's not a V naught, it's a V orbital. Okay, so we have 2 equations with 2 unknowns. We have a relationship between these 2 suckers here. So I'm going to go ahead and plug in, since I know VO, I'm going to plug in R orbital times the omega. That equals all that jazz. You know what? I'm gonna go ahead and get rid of that root value. I'm gonna square this side, square both sides here. So we get G ME over R orbital. And let's solve this. Here we're going to R orbital squared, omega squared equals GME over R orbital. And since we're solving for R orbital, let's go with cube. Bring this one up to this side, and we're going to divide both sides by omega squared. G massive Earth over omega squared. Just some geometry there. And we can plug those in. 6.67 times 10 to the negative 11. We got massive Earth. That sucker keeps coming up. 5.97 times 10 to the 24 kilograms. Divided by omega squared. 7.27 times 10 to the negative 5 squared. Time to calculate. All right. All right, I got a huge number here. We got 7.53 times 10 to the 22. And I was starting to freak out. I was like, wow, that's really big. Okay, but yeah, we got a cube root here. So we got to take the cube root of both sides. We'll raise it to the 1/3 power, right? And finally, we get an R orbital. It's cube root. So we got a 3. I'm just going to take that answer to the 1/3 power. And I got 42. 4.2. 4.22. Times 10 to the 7 meters. Okay, so it's up there. Geostationary orbits are way up there. That's one of our unknowns. And our last one, we'll plug it right back into here. If we multiply those two together, so that take that r and multiply it by the omega, so our value up here, 7.27 times 10 to the negative 5. Velocity of 3071. Let's say 3070 meters per second. There it is. Requirement for geostationary orbit, as you can imagine, it's the only location you can put these satellites that Earth can send and receive from and to. Okay, so it's going to fill up. And once those satellites stop working, you know, do you just leave them up there? It's called space junk. Space junk right there. All right, next segment, we're going to get into elliptical orbits. Now, elliptical orbits are not circular, but circular orbits are elliptical orbits. It's kind of one of those things like a square is a rectangle, but not all rectangles are squares. So just a little review about orbits. Circular orbit has one center, but it actually has two centers that are on the same place. Because if you look at an elliptical orbit has two centers called foci. And you can make an ellipse on paper if you take like a string and tape it to a large sheet of paper. It's kind of loose. Tape two ends of that string to 2 points on the paper. And then you stretch out the string so it's tight and put a pencil right there. As you trace that around, it's going to make that string is going to limit how far you can move the pencil. And it's going to make something called an ellipse. You see these two lengths of string. String stays the same length no matter what. And here it stretched all the way over as far as it could. And likewise to anywhere on the ellipse, if you add up this piece and this piece, it's going to be the same length. And that's kind of what defines the ellipse. So of course I drew a really sloppy looking ellipse here. But if you do put those 2 points at the same location, then that string will stretch out to the end and go back, and those two lengths will always be equal, and you'll have a circle. Okay, so this is like the pieces of the string there, and you'll run it around. So a circle is an ellipse with both of its foci at the same point in space. That's basically what the sun is to the Earth. But there are actually two foci in our solar system, and that's what gives a lot of our, at least for each planet, that's what gives our Earth in an elliptical or slightly elliptical orbit. At some parts of the year, some parts of our revolution around the sun, we're a little bit closer than at other parts of the year. And many other planets have a similar elliptical orbit. Some have a more elliptical orbit than others. And there are other objects that orbit the sun that aren't planets. They're much smaller, things like comets. There's a whole ice cloud that orbits the sun that's far, far out there. It's out where Pluto is. It's called the Oort cloud, O-O-R-T. That also orbits the sun. As you might know, that Pluto has a more elliptical, kind of a highly elliptical orbit. At some parts of the year, it's closer in than at other parts. And I'm not drawing a great one here, but if you look at this drawing, this sketch, you can see that this part up here is greater than this part down here. All right, so it's longer. And that's sort of what Pluto does. And with if I draw some circles that are a little bit better than that, we look at the one planet that we'd call like slightly inside of Pluto, and Pluto's is so elliptical that it goes inside Uranus's orbit and something like this. So if this is Uranus and this is Pluto, yeah, I said Uranus, okay, Uranus, like that sounds any better. All right, but Pluto sometimes hangs outside of Uranus's sometimes hangs out outside Uranus's orbit. I couldn't get the word orbit out of my mouth. I wasn't laughing about Uranus, okay? Gosh, I couldn't get the word orbit out. And sometimes it's inside. Now another object that we find zooming by every 77 years or so. This is our sun. Look at Earth's orbit here. Lots of orbits going on. Is Hayles Comet. It comes in way from out there, way the heck out in space, and hangs out around the sun for a couple of weeks before moving on. So that's a highly elliptical orbit. If we're looking at Earth's orbit around the sun, and take that sun as one of Hayles Comet's foci, this is not as exaggerated as it should be, okay, but here we're seeing Hayles Comet orbit compared to ours. So Earth might have a couple of foci really close in, maybe both even inside the sun. I haven't run the numbers in a while, I don't remember. But for Hayles Comet, definitely uses the sun as one of them. And is there another object out here? No. So the sun is at one of Hayles Comet's foci, and the other foci is just a point out there in space, way the heck out there at the end of its orbit. And that's what you'll usually find. Approximately, they'll have that star at one of the foci, and another one is at a different point. So sometimes it's within the star, but just at a different point other than the center. That's just a little bit about elliptical orbits. So how do we handle these? Let's take here's the problem. Hayles Comet has a highly elliptical orbit. Its closest approach to the sun brings it to an orbital radius of 8.8 times 10 to the 10. That should be a 10 to the 10th power meters. Now, AU is astronomical units. 1 AU is 1.5 times 10 to the 11 meters. And that is the Earth's orbital radius. We're using our average orbital radius of the Earth as the standard unit of distance for planets in a solar system. Okay, so AU. So its closest approach is almost half an AU, just a little more than that, while traveling at 70.6 kilometers per second. Determine the furthest distance from the sun the comet reaches, called its aphelion, if at this point it's traveling with a velocity of 1.17. So there's going to be a big difference in speed. This is not a circular orbit. Let's sketch it out here. This is the sun way in here, and this is our other foci for Hayles Comet. There's 2 points, 2 distances here. Its closest approach is right there, and its furthest approach, departure, there you go. The furthest departure is way out here. So we essentially have an inner radius and an outer radius, a long distance and a short distance and a long distance. And there's a velocity at point 1 and a velocity at point 2. Now this comet also has a mass to it. Remember that. It's got a mass to it. Now, in recent history and physics class taking, have you worked with some kind of properties that have some kind of quantity that has an MV and an R? Or should I say an R and an MV? If you're thinking, wait a second, isn't that angular momentum for a point mass? Yeah, it is. So before we move ahead, can we apply the law of conservation of angular momentum to this scenario? Well, to answer that question, is there any external forces causing torque to the system? Are there any external forces that may cause a change in momentum? And if we just look at the system as consisting of Hayles Comet and the sun, then no. Does anything change? Does anything external push on Hayles Comet to affect it? It's only really the sun's mass that's attracting it. Now, Hayles Comet if it ever came close enough to a planet, that planet could actually dislodge it from its orbit. We may never see it again, or its trajectory could change, and it might end up going somewhere else. All right, but thankfully, it seems to be pretty clockwork, so we probably don't have a comet that's in the same, oh, what's that word? Elliptic? Orbital plane? Same orbital plane. I think there's a fancy other name for that. But an object that's in the same orbital plane will likely be affected by other objects that are in that orbital plane, and their orbits might be affected by one another if they intersect. So I don't think so. If the Earth and Venus and Jupiter and Saturn and Uranus and all those planets orbit like this, if Halley's Comet orbits more like this, then it's not in the same plane. They're unlikely. It's unlikely to be affected by their orbits. That's not really an important point here, though. The important thing is angular momentum is conserved. We only have a Halley's Comet and Sun system. It's being affected by gravity. As it gets closer to the Sun, there's more and more of an inward force. So it gets slung around the Sun at these incredible speeds, 70.6 kilometers per second at the maximum. But way out here, Earth's gravity, or the Sun's gravity, the strength between the Halley's Comet and the Sun is much, much less. So its acceleration is less and less. But it doesn't escape the Sun's pull. It doesn't escape that gravitation from the Sun. If it was moving faster, it might sling off and never come back. If it was moving slower, it would have a less elliptical orbit. If it got slowed down out here. But it could change its dynamic that way. Actually, if it got slowed down in here, it changed the shape of that orbit. Big thing, though, is angular momentum is conserved. And at this particular point, the velocity is, I should say it from the other direction. If its orbital motion is in this direction, then at this point, its velocity is this way, and at this point down here, its velocity is that way. Do you notice how the radius and the velocity vectors are perpendicular at those points? It's our closest approach and furthest approach. What we have here is that L at 1 should be equal to L at 2. Should be equal to the angular momentum at any other point along this orbit. And that's the thing about elliptical orbits. You have a situation of conservation of angular momentum. All right, you can either look at this as I omega, where I is mr squared, and omega is v over r. And if that's the case, you just get rmv out of it. So because they are the cross product, gives us a sine theta, and theta is 90. Sine of 90 degrees is 1. All that means is R1 times mass of Halley's Comet times velocity at 1 equals R2, mv2. And I love this because it's so simple in the end. Once you understand that this is law of conservation of angular momentum, the masses cancel, and you get this cool ratio thing happening. R1v1 equals R2v2. And you could, you know, rearrange these. R1 over R2 equals V2 over V1. Kind of an inverse relationship there, but it's this simple. We plug in our closest approach, and you can use either AUs or you can use meters. I'll go ahead and use meters because that's what's given. At the closest approach, we got 8.8 times 10 to the 10 meters times its velocity, 70.6 kilometers per second. We're going to change that to meters. Or I'm just going to do times 10 to the third. All right. That'll be meters per second. Equals, what is its furthest distance? We've got to find R2. R2, where are you? Where could he be? Okay. I guess that's 3PO. 3PO, where could he be? Mark Hamill, you're my hero. You were always my hero. I think above Superman, and that's saying a lot. Because I ran around in Superman tights. Actually, it was just the underwear part when I was like 5. And I'm saying Mark Hamill is more my hero. E. 10. 8.8 times 10 to the 10 times. Let's work this out. Divided by 1.17 E3. 5.31 times 10 to the 12. There it is. Oh, I'm in purple. How did I get to purple? I guess it's more magenta. All right, the closest approach was our 8.8 times 10 to the 10. And our furthest is 10 to the 12. So it's a little less than 100 times the distance. 100 times the distance. Woo! All right, there it is. All right, elliptical orbits, very easy. R1 V1 equals R2 V2. And that's the end of the program.